will not be. Awesome. Hi, thank you guys for having me here today. As Jay said, my name is Cassy Davison. I'm here from Georgia State University, and I just want to tell you a little bit about my research and passion in life, which is searching for companions around cool stars. So for my talk today, I'm first going to just give you a little bit of background information about stars and planets very briefly. Then I'm going to talk about my thesis sample, and then give you some of the results from my radial velocity and astrometric surveys. So starting off, when I have basically the HR diagram with all the different mass stars here, you can see them categorized. A lot of people know the mnemonic of OBA fine girl kiss me. So our sun is a G2 star. So some people like to say it's an average, but it's still kind of small in this perspective. But even being small, still 1 million Earths could fit inside of the sun. So it's still rather large. But I'm going to look at even smaller stars, and I'm going to look at this M stars, which are the smallest and lowest mass stars. Here they are on the HR diagram. This gives us a lot of other relevant information. You can see the temperatures here. So when I said cool stars, it's because M stars are cold compared to the hotter blue stars. And one other thing that's really interesting is the lifetimes of these stars. That these hot stars, they burn through a lot of their hydrogen very, very quickly, and then therefore leave the main sequence very, very quickly. Whereas these M stars stay on the main sequence for a very long time and can have lifetimes. This is 10 to the 7, this is 10 to 11, up to 10 to the 13 down here. So it can be, 10 to the 7 to 10 to the 11 is a lot longer in time. So if we wanted to look for a place that might have formed planets, a star that might have formed planets around it, and not just a place that might have formed planets, but maybe a planet that has intelligent life and has a civilization, we probably want to look around stars that have been on the main sequence for a long time and would have that feasibility to do that. So M stars are very interesting targets. And around these stars, particularly what would be interesting is to search for habitable planets. There is the traditional habitable zone, which is where you would have liquid water. So for this, you can see for the sun, the traditional habitable zone would fall right there with Venus, Earth, and Mars. And we can basically look around other stars and calculate what the temperatures would be and predict where you would have some kind of a liquid around those stars. This traditional habitable zone, since these stars are a lot brighter and give off more energy, it's further out for the more massive stars. And then it's closer in for these red stars, the M dwarfs, which is a good thing because it's easier to find planets that are closer in to their host stars. So it's another reason why we should look around M dwarfs. So do you guys have an idea when I start talking about planets, how many of them have been found so far? Is this a shallow number? 1,000? Several thousand. Pretty good answer. Do you guys have an idea on how many Kepler candidates there are? I heard only a few. Are there other guesses? Thousands. There's actually a lot. So I actually have this slide. I updated it from January this year. And as of January, there were about 1,000 confirmed planets. So this is almost doubled in how many have been confirmed. And it's mostly due to the Kepler results. Like since Kepler's come online, they found lots of candidates. And we've had lots of follow-ups that have turned out to be validated planets. I also just wanted to make one special note, and then I'll come to the question. A lot of people, when they talk about planets and they got excited with finding the first one, it was in 1995 by Mayor and Quellis. It was a hot Jupiter planet, so it was a Jupiter-mass planet in a short orbit. But then after we started getting lots of these planets, we needed to make a good definition for what a planet was. We don't actually have a good definition on what an exoplanet is. We have a working definition that as we find more, we'll probably change from. But it's basically that that a planet should be less than 13 masses of Jupiter. So when you look back It was actually Dave Latham in 1989 who found an 11 times the massive Jupiter object. So it was in 1989 when the first planet was formed. Can I hear your question? Kepler, so they've looked at the transits in the data, and they've been able to see that there's definitely an object there, but they don't know all of the information with all of the inclinations, so they have to make sure that some of those might not actually be like a star, or one of them was actually a white dwarf candidate. Did you have another comment, Shay? Not only does a person go and confirm it, but they also then go collect radial velocity curves of the stars in order to determine what would be the inclination and if whether this is actually a planet or whether this is a brown dwarf or a low mass star. Yes, some people have done false positive surveys in which you would look to try to see if what their initial results were something different, and it's coming down to a lot of these are turning out to be planets. So with that, I'll say they are finding about 1.5 planets per M-dwarf is what the Kepler data results have. And so planets around M-dwarfs are common. M-dwarfs are also very common. M-dwarfs make about 75% of the known stellar galactic population. So unlike O-stars, which are really rare to see, M-dwarfs are everywhere. And they're very nearby. So that's what I want to focus on my sample. And a lot of these stars, M-dwarfs, have also been overlooked in many surveys. These stars, as you get to the later M's, they're actually very faint. So even going from the mid-M to a late M, you're looking at a star that's 100 times fainter in the optical. So that means that you'd have to collect 100 times more light and signal to get the same kind of quality data as you had gotten with a more massive M dwarf. So it's very hard to do these stars. These stars are also more active. So they have lots of spots or lots of flares on the stars. And these spots and flares, it can actually mask and it can pretend and it can look like what a planet would look like. So this is actually a radial velocity curve here of data. And this star had very active spots on it that made its radial velocity turn from going very fast to very fast in the other direction. So people actually thought this star had a planet. And then when it was done in another waveband, we actually saw that this star is a very constant star and not moving very fast. So M dwarfs have been really tricky in the past, especially as you get to the later ones, to search for planets. So that's exactly what I want to do, because somebody said tricky, and it sounded like trick or treat, Halloween, and I like costumes, so it sounds fun. So I'm looking around stars that are around the celestial equator that go from plus to minus 30 in DEC. They're all mid to late M dwarfs, so M3.5 to M8. They're nearby, so 10 parsecs is about 32 light years. And they don't have close companions. Because I like tricky, but not too tricky, and it would make it a lot more difficult if they had a companion to see the planet's curve on top of that. And the two telescopes that I use, one is in the north and one is in the south. In the north, I'm using spectrograph, and in the south, I'm doing astrometric measurements. So these two methods, they're complementary. The radial velocity method is going to be really great for finding planets that are edge-on in short periods, whereas the astrometric method is going to find planets that are face-on, and it's going to be in long periods of, 2+ years up to about 10. So I know Travis was talking to you earlier about the radial velocity method. Here's the spectrum down here. As the planet orbits around the star, it's going to cause the star to move as the center of mass changes for the system. And basically the spectrum is going to be blue shifted when it's coming towards you and red shifted when it's moving away from you, which is very similar. The radial velocity method, my advisor shows sometimes take radial out of it and just call it the velocity method, that we're just measuring the velocity of the star. And if the star is moving really fast in one direction and then moving really fast in the other direction and it keeps cycling through, we know that something must be causing it to do that. And if something's causing it, we can infer what that is and we can figure out what its period and what its mass is. So I do this with NASA's Infrared Telescope Facility, which is on Mauna Kea. It is very beautiful. You guys should have a class trip to Hawaii. Yes, yes. And the instrument I use is named Seashell. When I get the data, this is actually what it looks like. It's a snapshot from the telescope viewer screen. And I actually take two spectrums. There's an A nod and a B nod, because when you're doing infrared spectroscopy, a lot of times we'll have sky emission lines that are superimposed on our data, and we want to be able to take the A nod and the B nod and subtract them from each other to get rid of those sky emission lines. It also gets rid of the dark current and the bias. So we don't have to worry about any of those. We're going to correct for flat fielding, because not every single pixel reads the light coming in from the star exactly the same. And then we're going to apply a bad pixel mask for any of those pixels that weren't working after we applied the bad pixel mask. I'll go back to this. And then after that, basically, we have every single column right here. We're going to go add for each one of these pixels how many star counts we had, and we're going to add this up for each individual column. And then that's what you would see, that this would be one column's point here. So I have 256 columns. That would have been just one column going back. And I actually have two stars here. One of them is an A star, which Jeremy is telling me that he cares about. And then this is an M dwarf down here. This A star, it actually does not have any absorption features in the infrared. Anybody looking at this funny? I just said it didn't have any absorption features. Good. So I know you guys see that it's there. We actually have telluric lines from the Earth's atmosphere that are superimposed on the spectra. So basically, just because we're observing through the Earth's atmosphere, we have these lines. They're also superimposed here on this M dwarf, along with the M dwarf's regular lines. So we know where these telluric lines are going to be. We already know that. So we can basically compare where these lines are going to be compared to where our synthetic lines are going to be to see if these synthetic lines would move relative to where the telluric lines are. And then we can figure out what's the absolute radial velocity, so it's the velocity of the star, and then we can determine if the star's velocity is changing. So I did this for one target, which is here GJ729, and you see that my precision is within about 50 meters per second. With this, I could find objects that are about half the mass of Jupiter in periods between 5 and 10 days, which is what I was hoping to do when I started this project. And over here you have about another 25, 30 stars, and all of them, my average is around 100 meters per second, which will give me the same precision of finding hot Jupiters. I have not found a hot Jupiter yet, but I did find something else. And with this, when I first took this, I took these 3 data points within one single run. These 2 data points actually happen to have almost the same exact velocity. And then this one was completely different. So I first thought maybe there's something exciting, and then I was like, nope, nope, maybe you did a face palm. What did you do wrong? What could it be? So we actually had to rule out the possibilities, and we took more observations, and we were able to figure out that this star is a spectroscopic binary. Not only is this star a spectroscopic binary, GJ867b is the secondary in the system, and they know that the primary, GJ867a, is also a binary. So this star is actually the closest low-mass quadruple system to the Sun, because it has 4 components, and it is the only low mass quadruple system that we know about within about 75 light years. So these systems are very, very rare. And this D component here has a minimum mass of 61 times the mass of Jupiter. And if you guys remember, we classify brown dwarfs as objects that go up to 80 times the mass of Jupiter. So this object may be a brown dwarf, or it might be a very low mass star. We do not know the inclination of the system. Either way, I was excited when I found it. So for the other technique I use is astrometry. So can you guys all go hold your thumbs out in front of you like this? So I want you guys to go look at, I want you guys to wink. Close one eye and then close the other. And then do you see how your thumb moves compared to the background? We use the same exact technique in astrometry, but rather than using your thumb, we're basically going to compare how this star moves relative to the background as the Earth moves around the sun. So you can see here this star ended up on the right, and over here in July it ended up on the left. And we can do this to figure out the exact distance to the star. And then if the star is moving, then we can try to figure out if there's a planet or a companion around it. So I take this data down in Chile, which is also a very wonderful country that we should all have Jay pay for us to go visit. I think he's on there. And we use a 0.9 meter telescope. Anytime I go, it's always snowing. So don't take me on your observing runs because they'll probably be weathered out and you'll probably have to spend all the time at the beach instead. But it's a wonderful mountain to go on. And when we go and get data from the telescope, this is what it looks like. So this is our star field here. And basically we are going to go and choose a filter that's going to be in the optical to go look at these stars. And that target, we're going to want to have lots of stars close by our target star that have lots of counts. We're also going to want this, the field not to be very elliptical, where all of our stars, instead of being a nice circle like most of them are, that they'd be elliptical. Ellipticity could be that you have a binary in the field, or it could be some kind of guiding or tracking error that you made with the telescope that kind of just made everything elongated. So we don't want to use any of those images, and we want the thing to be less than 2.4 arc seconds. So after we've gotten all good frames, we're going to pass this data through our pipeline. We're going to untangle the parallactic, so the motion due to just the parallax and the Earth moving around the sun, and the proper motion of the star, just its motion in space, and then see if there's any residual motion left. And if this residual motion is in some kind of sinusoidal kind of motion, we can assume that something must be causing it to have this excess motion that could be in a companion. So here's one of my targets right here. That's a pretty flat line. It's on the level of my best precision. So you guys remember that my radial velocity precision was about 100 meters per second on average. This is the radial velocity, 84 meters per second. And this is my astrometric data of less than 4 milliarc seconds, is how precisely we know this position of the star, of its move, of where it is in space. So this star, it does not have any companions in long periods of, 6, 2, 3, 4, 10 years. And we know that it doesn't have a companion within about 100 days either from the radial velocity data. Yet, this star has been listed as a binary in the literature. So I just point this out, that sometimes if stars are listed, they are misclassified, and that if there's no data behind it, that maybe it's worth it to go look it up. Because this star right now has been in several surveys, and all they've said about it is that we are not going to follow this star up because it is a binary. This star could have an Earth mass target and is nearby, and we're not going after it because it was mislabeled. So it's important to look at that stuff. And my astrometric data is all in line with this 4 milliarc seconds. I think that's about my average precision there for about 25 stars. So my astrometric survey has not found anything yet. But here are some other targets here just to show you what our program could do. So this has a residual deviation of about 45 milliarc seconds, and it happens to be 2 low mass stars together. And then this star would have actually have been in my sample if it would have been an M8 instead of an M8.5. And this star has a T-dwarf companion, which is getting pretty close on the low end of brown dwarf companions mass-wise, just to show you that we are getting close to approaching to be able to find Jupiter mass companions if they exist. With my data so far, I've listed about 3/4 of the stars, and there are no objects that are about 5 times the mass of Jupiter and greater within periods of about 2 years to 10 years. So just a quick summary, my RV precision is below 100 meters per second. My astrometric precision is about 4 milliards seconds. I'm not finding anything, except I did find no planet. I did find the closest quadruple system to the sun, and one of my other targets ended up being a spectroscopic binary as well. After I had gotten some data on it and before I could publish, someone else published it as a spectroscopic binary. So they're out there. These stars haven't all been looked at yet. There's still more mid to late M dwarfs, and we could still find more companions. And just to leave you guys, if you guys have any questions, I don't only want to find planets one day, but when the technology's there, I'm going to find extraterrestrial life maybe in 20 years. So I just want to leave you guys out there that there's different kinds of creatures out there that if we open up our minds, lots of stuff is there. This is who I want all of you guys to know for Halloween. Right here. So no light, but still heat. No light. Well, the planets all that they're looking at would be close enough that they would have starlight. I don't know if there are people taking calculations of just what's the thermal heating from the planet, but I know that people go with the starlight to go calculate what would be the traditional habitable zone. But a lot of people have started also thinking that maybe when you start looking at other creatures, not everything is methane or like carbon-based. And when you start including all of that, I think a lot of people aren't discounting life on, where you might have like ammonia or different kind of things. I don't know if people, the habitable zone is tricky. I don't know if they've extended the definition or if they just extended out of the traditional. I don't know. Does anybody here know if they include heating from the planet? And it would be really, yes.